We're the drone-based radar intelligence soil subsurface characterization MQP team. Our goal was to develop an intelligent moisture characterization via drone-based radar signal and data analysis. So with climate change being as big an issue as ever, farmers need to know where to properly irrigate their soil in order to avoid water and soil mineral waste. So to counter this, we attached a sensor to a drone that would send a ground penetrating radar signal into the ground, and the received signal would create a root zone moisture map for farmers to use. And ideally it would be this 10 kilometer by 10 kilometer plot as shown here that would show where soil is overhydrated by the dark blue, properly hydrated by the middle, by the regular blue, and then underhydrated for the light blue. And farmers could use this in order to know where to properly irrigate their crops.
We've had many accomplishments throughout this project over the last year, including the design of our ground-penetrating radar, which you can see in that photo. This was reduced in size and weight over many models to be the one that's found on our Aurelia X6 Max now. The data measurement campaign with the SFCW waveforms and implementing the SFCW radar onto the mobile drone were also very significant. And lastly, developing the machine learning model that pairs with the data to turn everything that we read from our radar into meaningful results. The result of this was reducing the amount of time that it took to capture a measured field, which was a few hours to do 10 feet before, which can now do several acres in a fraction of the amount of time.
Our measurement campaign began with simulating soil moisture data with GPR Max, and from the simulated data we were able to determine the CNN model was the one we wanted to use for this type of data. So our actual measurement collection was simulating a drone flight by having the radar attached up here, going back and forth across this small section of land, and we take measurements with observers and without observers in order to eliminate the environmental noise. So we get measurements that were just accurate to the soil, and then we label these soil accurate measurements with moisture probe data taken from the same location, and then we were able to get accurate measurements of the soil moisture with the radar.
So we transmitted an SFCW signal, which we chose for its high resolution and wide bandwidth, which we did from a range of 400 megahertz to 1.2 gigahertz, with increments of 100 megahertz each for our recordings. We could then visualize this reflected signal with a real-time spectrum analyzer data. We then could pre-process both the moisture probe data and our spectrum analyzer data. So for the spectrum analyzer data, we turned it into spectrograms that we made sure were each 128 by 128 pixels. And then we could pair those spectrograms with our moisture probe data, which we had normalized so the model can understand what's going on. We could then split that paired data using K cross-fold validation into 5 sets. So then we could split it into our training, testing, and validation set. And then we would also use an atom optimizer within our CNN to avoid overfitting of the data. So we could then pass these data sets through our CNN. For our first convolutional layer, we chose 32 features for the low-level outer edge areas of our image and for feature extraction. And then for our second convolutional layer, we chose 64 for more high-level features that could be extracted from our spectrograms. Which would then output the 73 objects, which is shown here below, of our CNN, which is each of the depth, moisture percentages, and millivolts. We could then use a ReLU function to show our training and validation loss here, showing that the model is learning as it takes a pass over each of the data, which is the epochs on this part of the slide. That it's learning from the data, and that it has about a 98% accuracy with a 2% loss. We could then show that we have our MAE was about 2.2 units on average for both the moisture percentage and the millivolts, which we could show on a QQ plot, which is a normal distribution, and each of the 73 dots show how far away it is from getting that prediction 100% accurate and correct.
Our future works include enriching the limited moisture probe and SFCW data set by measuring grounds with different textures, which will train a model that has a better prediction accuracy in terms of both the moisture levels received and objects in the ground that it picks up that can cause unwanted noise.